There are two other classes of reaction that can happen when we take an anion and a cation and combine them together. We were talking about precipitation reactions. These are also called double replacement reactions because they're swapping partners. Let's see. Double displacement or double replacement reactions. I give up. I keep hitting the wrong thing and, oh, there it comes back. There. Double displacement reactions. And I don't know where that came from. Good grief. So acid-base and gas evolution reactions, we can think of them in the same way, about looking at the ions that are formed by the compounds, swapping the partners, and seeing what happens. Acid-base reactions are also called neutralization reactions because the acid and the base neutralize each other. And when that happens, we get water and a salt. And then the other type is a gas evolution reaction, which produces a gas often seen as bubbling. What I just showed you there with the acetic acid mixing with our calcium carbonate precipitate was a gas evolution reaction. We saw the bubbles forming. So we have to talk real briefly about what acids and bases are. The Arrhenius definition of an acid is that it is a substance that produces hydrogen ions in aqueous solution. So hydrochloric acid, HCl, we put it in water, that's aqueous. We get hydrogen ions and chloride ions. But what's really going on is that the hydrogen from the acid is being donated to a water molecule. Really, what is a hydrogen ion? What's in the nucleus of a hydrogen atom? One proton. And how many electrons does a hydrogen atom have? One. So a hydrogen ion has lost one electron. What's left? A proton. Just a proton. It's a naked, bare, little, tiny proton. It's like a 3-month-old baby at Disneyland. It's too small to be out by itself. You don't see 3-month-old babies running down the sidewalk, right? They can't. Well, this hydrogen ion is too small to be out by himself. So what he actually does is he hitches a ride on a water molecule. And when you put an H plus onto H2O, you get H3O plus. And this has the name hydronium ion. And this is what actually is in the water when an acid is present. So we need to understand that that's what's actually going on, but chemists usually use H plus and H3O plus interchangeably because using H plus makes the equation so much simpler. And we all understand that, yes, there's someone holding the baby. Well, we're just talking about what the baby did. He went here and there. Somebody was carrying him. The hydrogen ion goes here and there, and we understand that he's actually riding on the back of a water molecule. So that's the hydronium ion. A base, by the Arrhenius definition, is a substance that produces hydroxide ions in aqueous solution. So sodium hydroxide. This is a soluble ionic compound. Sodium compounds are soluble. It produces sodium ions and hydroxide ions. It's a base. There are other bases like NH3. You look at NH3 and you wouldn't necessarily predict that that's going to form hydroxide ions, right? It doesn't have any hydrogen in it. I mean oxygen. It's got hydrogens. It doesn't have any oxygen in it. So how could it make hydroxide ions? Well, it makes hydroxide ions by taking a hydrogen off of a water molecule. Is that in the next slide? No, that would be too convenient. So the way that works is NH3 plus H2O forms ammonium ion and hydroxide ion. Because water is funny stuff. Water will hold on to the proton for you, but if you need a proton, it will give one up. and then you form hydroxide ion. Polyprotic acids. Poly meaning many, protic meaning proton, hydrogen ion. So polyprotic acid has more than one ionizable hydrogen. Sulfuric acid is a diprotic acid. It's got 2 hydrogen ions. And what happens when you put it in water is, because it's an acid, it will release a hydrogen ion. So H2SO4 plus H2O, it will donate a proton to the water molecule, forming that hydronium ion, and then you're going to have the hydrogen sulfate ion that's left. The first proton is a strong ionization, meaning it all ionizes. This hydrogen sulfate losing the second one is weak, and so this is kind of a back and forth thing. See, now I'm going to be really inconsistent there. This hydrogen ion can come off, leaving sulfate ion. We understand that this would be riding on a water molecule. But it only does this a little bit. So we're going to see most of it is this way. And there are some bases that also produce 2 moles of hydroxide per mole of base. I think magnesium hydroxide is soluble. Magnesium hydroxide would dissociate into magnesium 2+ plus 2 hydroxide ions. Does that make sense? You can tell that from the formula. Well, what happens in the acid-base reaction is that the hydrogen ion from the acid combines with the hydroxide ion from the base, and that makes water. So here we've got the acid, HCl. If we think about, well, what ions does that make in solution? Makes H+ and Cl-. And the base, sodium hydroxide, makes sodium ions and hydroxide ions. And then we do that partner swapping thing. And we get hydrogen ion with hydroxide ion, and we get sodium with chloride. And so the same thing we did with the precipitation reactions, H+ and OH-. And I'd say, well, yeah, but that would be HOH. Well, that looks dumb, doesn't it? That's H2O. Makes water and salt, salt being an ionic compound. If we look at the net ionic equation for this, it's H+ plus OH- yielding water. The sodium ion is aqueous and the chloride ion is aqueous, and over here sodium chloride is aqueous. Nothing happened to the sodium or the chloride. It was just the hydrogen ion and the hydroxide ion. So what we'll see is that this is the net ionic equation for most acid-base reactions. All comes down to the same thing. That's a picture showing that happening. We need the pictures because when you watch it happen, you can't see anything happening. Just waiting for the train to be done. Common acids and bases. These are the strong acids, those guys right there. You need to remember which ones they are. Strong acids. Hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric, sulfuric, and perchloric. These are 2 other common acids, but they're weak, meaning it doesn't dissociate well. So you'll get a little bit of hydrogen ion, a little bit of acetate ion, but mostly the acetic acid molecule. And hydrofluoric acid also dissociates a little bit. These are common bases. And if you notice, what they have in common is most of these are metal hydroxides. This is the one example we'll see that's not. This is a weak base. Ammonia is a base even though it doesn't contain any hydroxide. And here's the reaction that I showed you earlier. It takes a hydrogen ion off of the water and it forms hydroxide that way. And water can be an acid and a base. I think we get to that in this class. I can't remember. So let's write molecular and net ionic equations for these reactions. What kind of a compound is HCl? It's a strong acid. And what kind of a compound is barium hydroxide? It's a base. So we have acid and base. Knowing that, we can almost just write the net ionic equation right there. But we won't. We'll do it the hard way. This is a strong acid, so I'm going to separate into ions. H plus and Cl minus. And barium hydroxide is soluble. That's Ba, 2 plus, and OH minus. And then what happens to predict the products is we're switching partners. And we've got H plus with OH minus, and we've got barium 2 plus with chloride. And then we predict the products. H plus and OH minus is H2O. What's the state of water at room temperature? It's a liquid. And then barium chloride, the formula will be BaCl2. Is that soluble or insoluble? I think barium chloride. Oh, okay. I was thinking it was insoluble, but apparently it's soluble. So aqueous. So that's the molecular equation. Is it balanced? Is it balanced? No, it isn't. What's wrong with it? The H's are messed up. So is the chloride. Here we've got hydrogens and oxygens kind of all over the place. We don't want to start with them. We want to start with something else. So we've got 2 chlorides over here. So let's fix that first. We'll put a 2 here. And so we've got 2 chlorides, and the bariums are okay. And now we can deal with the H's and the O's. So there are 2 oxygens here. And so we need 2 water molecules so that we'll get 2 oxygens over here. Now we've got 4 hydrogens, and here we've got 2 hydrogens there, and 2 over there is 4, so we're good. So there's our molecular equation. Now when we're crossing out spectators, can we cross out H plus and OH minus? No, because these make a liquid. So those guys are together. Those guys are together. But these guys are ionized. These are aqueous. These are aqueous. These are aqueous. So we've got the barium that didn't change and the chloride that didn't change. And what's left is H plus OH minus going to H2O. And yeah, this would have 2's in front of it because there's 2 H's and there's 2 OH's and there's 2 waters. But do we need that for balanced equation? What if we divided everything by 2? Is that balanced without the 2's? Yeah, it is. You want to see the other one, or you want to just go on? We want to sit here and stare at you until someone's willing to say something. Do the other one? Okay. H2SO4. Is that a strong acid? It is. So we're going to separate that into ions. Well, I'm forgetting what I'm doing here. We're predicting products first. So that's H plus and SO4 minus. And this is aqueous. That's lithium and hydroxide. And we're going to swap partners. And we're going to get H plus with OH minus. And we're going to get lithium with sulfate. So H2O is one of our products, and lithium sulfate is the other. Is lithium sulfate soluble or insoluble? Insoluble. It's soluble, so I'm writing an S. That's not right. Easy mistake to make. S in parentheses means solid. Soluble would be AQ. Is that one balanced? No. You got 2 lithiums here. So we need to squeeze a 2 in right here. And then we're going to end up with a 2 here. This acid is diprotic. It's got 2 hydrogen ions. That means when we get done with our balanced equation, we're going to end up with 2 water molecules, one from each of those hydrogens. A similar thing happened up here. This base has 2 hydroxide ions. Each of those is going to go into 1 water molecule, and so we end up with 2 water molecules. If this was something like lithium hydroxide, we'd just end up with 1. So what's our net ionic equation for number 2? H plus plus OH minus forming H2O liquid. So sulfates didn't change, and lithium didn't change. It was just the hydrogens and the hydroxide making water. Any questions?